transforming functions, function families. Investigation. We will use GeoGebra graphing calculator to complete the following tasks. In part A, we have to comment on all functions of the form y equals 2x plus b. Okay, so these functions here represent a family of functions. So let me write it down. So y equals 2x plus b is a family of functions because b is a parameter which can take on any value. For example, if b is, for example, 0, then the function would look as y equals 2x. If b is, say, 1, it would be y equals 2x plus 1. If b was negative, for example, b would be equal to, say, minus 2, it would be y equals 2x minus 2. Okay, so many functions of this form, they form a family of functions. This is the concept of a family of functions which you have to understand, that there is a lot of functions which are somewhat related to the function y equals 2x, where there is the zero value of this parameter, and we have to find what is the relationship. We have to comment on the relationship between all these functions. Okay, so to do it, we are going to use the GeoGebra calculator, and I'm going to type in this function 2x plus b. Okay, but before that, I need some way how to change the parameter, and therefore what I do is I just type in b, and GeoGebra creates a slider for me. So this is the slider, and now I can write the formula y equals 2x plus b. And here it is, here is the function 2x plus, and in our case it's 2x plus 1. We can change what is displayed here by tweaking this setting, so we can also show the value, and you see that the function is 2x plus 1. Now, when you change the slider, for example, increase the value of b, you can see that the entire line moves. For example, now when b is 5, it is passing through this value 5 at the vertical axis, through this point 5 here. Okay, if b is decreased, for example, to number 3, like this, the line passes through the point with coordinates 0 and 3. So it seems that all these lines forming the family of functions are parallel to each other. The only thing that is different for each of those lines is the point at which the line intersects the vertical axis, and the point has the vertical coordinate, the y coordinate, exactly equal to the value of the parameter. Okay, so this is all we can say about this first family of functions. All of them have the gradient of 2, all the graphs are lines, and for all of them it is true that they pass or they intersect the y-axis at b. Okay, now let us look at the other part, at part b. We have to comment on all functions of the form y equals a times x plus 2. Okay, so what functions do we mean? For example, we can have the function when a is 0, we can have the function y equals 0. Or when a is, say, 1, we can have y equals x plus 2. Or when a is negative 1, we can have y equals minus x plus 2. So you see, there is always plus 2 there in the function, but the thing that it differs is the coefficient in front of x, and this makes a lot of functions which we can think about. So let us go back to the GeoGebra and try to type in this family of functions. So I will just delete the previously typed in things, and now I need the slider a, and the function y equals a times x plus 2, like this. Okay, so this is the function. Again, let me tell the computer to show also the equation. Here it is, y equals x plus 2. We can move it somewhere to a more visible place. Okay, let it be here. Now, When I set the value of the parameter a to 0, you see you get the line, but this line has the equation y equals 0x plus 2, it's just 2, and it's parallel to the horizontal axis. It goes in a horizontal direction. When I increase a, it becomes more and more sloped, or it's more and more steep, and it increases from left to the right. So now a is 1. Well, you may well remember that the value of a here in this function, this is the linear function, represents the gradient. So the idea of gradient is as follows. If you move from one point of the graph 1 unit to the right, then you have to move 1 unit upwards to get back to this line. So therefore, this is the gradient. 1 is the gradient. If I set a equal to 2, like this, the line becomes even more steep. And again, when I move from this point 1 unit to the right, I have to move 2 units upwards to get back to the function. And the reason for that is the fact that the gradient is 2. What happens if gradient is negative? When then the line is decreasing like this. For example, when the gradient is negative 1, then you start here at one point of the line and then move 1 unit to the right, and you have to move 1 unit upwards, well, minus 1 unit upwards, which is the same as 1 unit downwards, to get back to the function. If a is, say, negative 2, like this, then you have to start here, move 1 unit to the right, and then 2 units downwards to get back to the function. So all these functions here, for all the different values of a, are linear functions. When a is positive, they are strictly increasing. When a is negative, they are strictly decreasing. And the value of a is identical with the gradient of all these functions. Okay, so this is what we can comment on this family. Now in part C, we have y equals ax squared, where a is not equal to 0. So for example, we can have the function y equals x squared, or y equals 1/2 x squared, or we can have y equals minus x squared, or we can have y equals minus 1/3 x squared, and so on. So all these functions represent a family of functions. All of them are quadratic functions, and the only thing that changes here is the value of a. Let us investigate. So we can leave the slider as it is. I will just rewrite this function. So it's the function ax squared this time. So here it is. Let me set the slider for the value of 1. So this is the typical quadratic function y equals x squared, 1 times x squared actually, as you can see yourself. Now if I increase the value of a, the parabola or the branches of parabola become steeper. So for example here a is 2. If a is 3, it's even more stretched away from the horizontal axis. If a is 5, even more so. If a is negative, however, the branches of the parabola will then go downwards like that. It's going to be concave downwards, and for example, when a is negative 1/2, you see how it looks, what it looks like. Instead of passing through the point with coordinates 1 and 1, which would be the point through which the parabola y equals x squared passes, this one passes through the point with coordinates 1 and negative 1/2. Okay, so this is also a stretch, but it is combined with the reflection about the x-axis. So for example, when a equals negative 2, like this, then we can say that the parabola, the original parabola y equals x squared, is first reflected about the x-axis, and then it's stretched twice in the vertical direction away from the x-axis. Okay, so this is for part C. Now in part D we have something familiar again, y equals x minus h all squared plus k. So you might remember that h and k have to do with translations. Okay, y, for example, the function here might be just y equals x squared. It would be true for h and k being equal to 0, or we can have y equals x minus 1 squared plus 2, and so on. Many different possibilities there. Okay, so let me try to investigate and actually review what you should already know. So I will remove everything from the construction here, and let me start with the sliders. So h is the first slider and k is the second one, and the function is y equals bracket x minus h end of bracket squared plus k, like this. Okay, so this is the function. We can tell the computer to show us also the formula for the function, like this. Now it's the function here is x minus 1 squared plus 1. Let me set both values to 0, like this, and you see that it's the original parabola y equals x squared. Now when I increase h, it is translated to the right by the same number of units as the value of the parameter. So for example, when h is 3, it is translated to the right by 3 units. If h is negative, then it's translated to the left, like this. This time it's translated to the left by 3 units. When, on the other hand, the k is tweaked, so if we change the value of k, let me set this back to 0, however, okay, when we change the value of k, the entire function is translated either upwards for positive values of k, for example, now k is 4 and it's translated 4 units upwards, or it may be translated downwards. When k is negative, like -2 for example, then it's translated by 2 units downwards. So these two parameters, h and k, have to do with translations, and we translate either to the right or to the left, or upwards or downwards. Okay, so this is the part D. And finally we have the function in part E, and in part E we have y equals k over x minus m plus n. So this is also something you might be familiar with. It is actually the rational function in the form ax plus b over cx plus d. Well, it can be transformed to it, and it has to do with the simplest case in which m and n are 0. So in this case the function would be, and k is 1, and the function would be 1 over x. And then when you change the values of k, for example, you take k equals 0, you can have y equals 2 over x, or you can have y equals minus 3 over x, and so on. And now when you change m and n, you can end up with some complicated functions. For example, y equals minus 2 over x plus 1 minus 3, like this. Okay, so all these functions in this form are represented by this family of functions. And now let us model it here in GeoGebra again. So I'll have to delete, however, parameters. I will leave just k, so k is important, we need it, so this is it. Now I need m, slider m, and the slider n, and now the function is y equals, now it's k over, we have x minus m plus n, like this. So this is the function. Now let us tell GeoGebra again to show its formula. Here it is, it's 1 over x minus 1 plus 1. Now, when I set m and n to 0, so to get the simplest case, okay, the simplest situation, it's the basic function, and k is 1, so I have just a reciprocal function. Now, when k is increased, I get a stretch. This function is stretched away from the x-axis. For example, when k is 4, then the function is stretched 4 times away from the horizontal x-axis. Okay, let me set it back exactly to 4. This point, 1, 1, was the point lying on the original function y equals 1 over x. And now, instead of the y coordinate being 1, it's 4, because it was stretched away from the x-axis. The same is true for the points on this side, on this branch of the hyperbola. Now, so we can stretch it. We can also take negative values of k. In this case, it's a combination of reflection about the x-axis and subsequent stretch. For example, when k is -2, like this, let me set it back, yeah, now, when k is -2, then I have to take the original function y equals 1 over x, reflect it about the x-axis. This will bring this branch to the fourth quadrant, and the branch from the third quadrant will move to the second quadrant, and then I have to stretch it twice away from the x-axis. So the point which would have had the original coordinates 1, 1 now has the coordinates 1 and -2, like this. This is all what you know. Now, when I tweak the values of m, the m, when it's increased, the entire function translates to the right. When m is decreased, it is translated to the left, and even like this, m is -5, for example. When I do the same with n, increasing n means shifting the whole graph upwards, translating it upwards in the vertical direction, and when I decrease n, the entire graph is translated downwards. So this is what you already should have known about all these function families. We have studied those in previous chapters. So in what follows, we will talk in more detail about these translations, stretches, and all other, and also reflections, and we'll solve more problems.